me show you how to be a good breezy and change your predictions after.
I've looked at the the website, of course, for BoTorch to prepare the episode, and now I wanna find a use case, to try that up. Because that looks really cool, and also I really like the API for users. It looks very well integrated with PyTorch, as you were saying. One thing I'm curious though is, so yeah, if you fit your model on PyTorch and then want to optimize with BoTorch, it's going to be super easy. What if you used a PyMC model, for instance, and then you get a posterior distribution? Can you just come with your posterior samples and plug that into BoTorch, or would that work differently?
Yeah, it's a good question. So basically, we assume that our inputs are torch tensors. Of course, you could use PyMC or any other thing to convert it to a tensor and stick it in. I think what you'll lose is the differentiability and the end-to-end kind of like autograd that you could compute on this. But if you do have a model and you can sample from the posterior distribution conditional on like whatever input you stick in, then you could take those samples and put them into an acquisition function. I think there would be a little bit of manual work to make this work, but the fundamental setup of the MC acquisition functions will allow you to kind of like compute things like Monte Carlo EI or whatever other version there is using that. Now, the thing that you lose that is one of the nice things that we have in BoTorch is, since you can't differentiate through those samples, something we do with the reparameterization trick in BoTorch, you'd have to like optimize that acquisition function without having access to gradients, right? So you'd basically have to do like a 0th order optimization over the acquisition function, which is fine if you're in low dimensions, but if you have a complex and high dimensional problem, that can be hard to optimize, because gradient-based methods are just much better in these higher dimensional spaces. I mean, that's how we fit neural nets, right? So yeah, I think it will generally work, will require a little bit of adaptation, but you're losing some nice features.
Okay, yeah, so you recommend mainly, like, the easiest case for people to at least get a feel of how that works would be to have a PyTorch model and then use BoTorch on top of that.
That's right. I mean, I should say that BoTorch also comes with like models packaged in, right? Like, it's not that you have to like bring your own model. So we have a bunch of high quality implementations of Gaussian processes, and there's a couple of other examples on other models on our community setup, and so you can use those out of the box, right? If you don't want to like go deep into the modeling, you can use that. So there's enough stuff there to like just assemble an optimization loop that will generally work pretty well without you like having to bring your own. I think the thing you need to do around it is like the orchestration. But I guess with the flexibility that you have is you can bring your own model, or you can bring your own like acquisition function implementation.
Mm-hmm. Okay, yeah, and actually this is a perfect segue for me to ask you a question I had planned also, which is, you built BoTorch on top of PyTorch, and as you alluded to, GPyTorch, which again is amazing, and it's going to be in the show notes. And listeners know I have a very close history with GPs, and I love them, so GPyTorch, definitely appreciate that. HSGPs also have changed my life. Now you can use GPs for much more, many more models, and many more use cases without waiting for hours for them to sample. So it's really absolutely incredible. I use them a lot in PyMC to have modular models, so not only GPs, but you can build other parts of the model with non-GPs part, and then you can use the GPs for nonlinear parts. And HSGPs really have changed the game on that, because you can also make them hierarchical. So that's really awesome. As soon as I see something with GPs in there, I get curious. So thanks so much for GPyTorch, and also for adding that in BoTorch. But I'm wondering, why was that interesting for you as the developers to build that on top of PyTorch and GPyTorch? Like, what advantages and also I'm guessing what headaches came from building on top of a deep learning stack instead of writing a bespoke framework. And if you hear some barks, folks, that's not Max. That's Max's dog. That's here on the picture. If you're on YouTube, you can probably see him or her. Beautiful dog, Max.
This is Keola. I mean, his sister Kaiko is outside, and she's barking up a storm, and he's just being supportive. Sorry about the noise, but yeah, they're quite energetic and vocal.
Yeah, that's perfect. I mean, that's the charm of live recording a podcast. So welcome to the show. So yeah, if you wanna, did you get my question about?
I did get your question. Yes. So okay. Yeah. So I mean, I really wanted to have a differentiable programming basis, right? Like I wanted to be able to use auto differentiation because I've spent a lot of time writing gradients by hand in like a previous stack, and it was kind of like a pain, as most people can imagine. And so yeah, I really wanted that. And I also really didn't want to like implement AutoGrad from scratch. So it was basically, PyTorch was an obvious core foundation for this. TensorFlow could have been as well. I guess this is a while ago, so JAX actually really didn't exist yet then. But PyTorch was in-house at Facebook, right? So we worked pretty closely with some of the PyTorch folks to actually also release BoTorch. I mean, we're part of the PyTorch ecosystem and in the PyTorch GitHub org. So it was basically just, hey, I needed like differential programming. Who has a cool framework for that? Oh, they're not sitting too far away from me. I should talk to those guys. And so that's basically how it started. And by the way, I do take full credit for PyTorch winning like the AI framework wars. Just BoTorch did that for them. No, just kidding. But so that's like the PyTorch part. And then as to GPyTorch, Gaussian processes are kind of like the go-to model that you'd use for Bayesian optimization. I mean, there's lots of alternatives around. Some of them I mentioned that cover certain use cases, but certainly at the time, like GPs were it, and for the majority of use cases, we still use them today. So I basically needed like GPs built on PyTorch, and that made GPyTorch a pretty obvious choice. And so at the time there was like an alpha version out there. I reached out to the developers, Jake and Jeff. So shout out to those guys. And we worked together on figuring out like how can we make this work for Bayesian optimization. That was kind of like the genesis of why PyTorch and GPyTorch are kind of like the foundations for BoTorch. But again, it's the PyTorch part is kind of pretty deeply integrated, so it's sort of like not that easy to use it without PyTorch. But the modeling abstractions that we have do not require you to use GPyTorch, right? So if you have, a Bayesian neural net or something else that you want to use, you can stick that in.
Mm-hmm. Yeah, this is super cool because like if you can experiment with some GP models easily out of the box with BoTorch, like this, from a user perspective, that's really easy, and I really like that because I have kind of a similar background to yours, which is where like I've been working in industry for years, and also I'm an open source developer, so you focus a lot on the consumers of your code. And it's like, okay, well, we have that problem to solve, but the goal is not to write a paper. The goal is to actually solve the problem and make it possible for people to use your solution. So thankfully, more and more papers now in the academic side, they come paired with an open source, at least open source repository, and more with a corresponding Python package that you can use and reproduce the analysis, which is great because otherwise most of the time people can't use what's in the paper. But yeah, like often my bias is very much on, okay, but how are people who don't really know all the nuts and bolts of that problem going to be using that? And so yeah, as you were saying, GPs are so versatile and and really good also most of the time at prediction stat. If you can make that easier for people to use, that's really a huge bonus in my eyes. Actually, a bonus question for you on that is, when would you recommend people use GPyTorch, for instance, like independently of BoTorch? Like, what kind of problems would you say GPyTorch is really excellent at, and what types of problem would you say maybe here it's not gonna work that well, or maybe here it's an overkill?
Yeah, that's a good question. I mean, I think GPyTorch has a similar design philosophy as BoTorch, and I guess and PyTorch for that matter. And that is kind of like also being so like research focused and allowing people to like easily subclass and extend and use their own. So certainly if you want to do that, it's a great framework for doing that. If you just want to fit a standard kind of like GP with like a matern kernel and like, uninformative priors on some data, and you want that to be fast and you don't want to have to deal with other things and overhead, you don't necessarily need to use GPyTorch. GPyTorch provides you a lot more flexibility. I think the thing that GPyTorch was built around initially by Jake and Jeff was using kind of like iterative linear algebra methods, so like Krylov subspace methods. So linear conjugate gradient solves rather than using a Koleski decomposition to compute to solve kind of like the GP equations. And so whenever you have like structured matrices, whenever you want to run things on a lot of data on the GPU, that is kind of like one aspect. And of course, since then there's been a lot of stochastic variational GPUs and other kind of like sparse GPU methods that have been integrated there. So there's a decent amount of like recent research work that also finds its way into GPyTorch on GPs. So I think those are the cases again where GPyTorch is a great package. I will say there's like some overhead in how the internals are being written that kind of like are necessary to handle structured matrix representations. And so that overhead, if you just work with like in a very small data regime with pretty little data, 50, 100 data points or something, and everything's just like dense matrix and everything's fast just by running it on optimized kind of like Koleski methods and so on, then there's overhead, right? Like it's not going to be necessarily as fast. So it's a little caveat, but in general, I think it's a great library.
Yeah, completely seconded. And how does it work for priors? Like, can you use, because you were mentioning mainly uninformative priors, can you make the models more informative in GPyTorch if you want, if you have good priors? Because I know that can be very, very important for GPs to be able to sample well. And also, can you combine any GP parts of the model with any non-GP parts?
Yeah, so I guess priors, there's the prior in the sense of like the prior over the hyperparameters, and then there's kind of like basically the GP priors, right, the kernel and the hyperparameters. So if you want to, depending on whether you do a map estimate or like a fully Bayesian implementation, it's pretty easy to stick in, different priors over, say, like the length scales or other aspects. So that is reasonably modular as well, so you can pretty easily do that. I do have to say I missed the second part of the question again because my guys have been barking again here.
So that was the prior part, and as you were saying, I was referring to mainly the hyperparameters of the GP. So let's say you have a matter kernel, as you were saying, so that would be the length scale and the amplitude, and most of the time it's, especially if you want a full Bayesian estimation of that, you really want some prior information in those, because they are like, let's say, like weakly unidentified in the model most of the time. And the second part of my question was, can you combine model parts in GPyTorch? Like you have a GP and then the other part of the model is something else, like a classic linear regression or something like that, where you add an external covariate.
Yeah, no, for sure. I mean, and it's in the same sense done in a very modular fashion, similar to BoTorch. And so, if you do want to stick that, neural network feature extractor on top of your GP and put it in there, you can. Yeah. So, very much working in the same kind of like fashion as BoTorch, modular design. You stick it in, and then differentiability and autograd will help you, and then you can do things. You can like jointly fit. So like a classic example would be like deep kernel regression essentially, or deep kernel learning, I guess is the term, where you have some neural network feature extractor and you basically like put a GP on the features. So it's very easy to do that. You can kind of like use a pre-trained feature extractor and then only fit the GP hyperparameters. Or you could like do some fine tuning with both. So it provides a lot of flexibility, similar to BoTorch.
Yeah, this is really cool. And by neural network feature extractor here, are you referring to, for what I understand from that, but you tell me if I'm wrong, is you have a lot of features, you don't really know how they relate to each other, so then you first fit a neural network on that to understand basically how the features relate to each other and maybe if some of them are redundant. And then once you have that subspace, you only fit the GP on that subspace of the features?
Yeah, basically. I mean, I guess the question is it like a supervised or so like an unsupervised type of embedding? But ultimately, like you have some high dimensional space, right? You want to embed it in a low dimensional Euclidean space so that you can like easily put a GP on top of it. So that's what I mean by that. And like you can either just jointly train this, but you'll need a decent amount of data, and there's some, difficulties around that. Or you can, what we see often in cases where people are using things like molecular design or protein design, they'll kind of like have a lot of data, do some, maybe like a variational autoencoder or something, right, where they basically have some latent space that they can kind of like train without necessarily the GP component. And then once you have that mapping from like this high dimensional descriptor space of what it is down to a latent space, and then you stick like in a GP model on top of that. So in this case, you'd be like doing the pre-training of that embedding, and then you're using that as a tool and to basically take this high dimensional input, stick it into the low dimensional space, and then work on the GP on top of that.
Right, yeah, okay. Yeah, that makes sense. Yeah, because you want to reduce the dimensionality as much as you can before fitting that, before fitting the GP. Yeah. So that makes sense. Okay. Yeah. And actually, let me ask you the same question with PyTorch. So we've seen in which cases GPyTorch is very interesting, but we haven't talked a lot about PyTorch actually on the show. So even though it's a huge package in the Python ecosystem, it's more tangentially linked to the Bayesian framework. So I think it's a great occasion also to tell listeners here, well, in which cases would they want to give PyTorch a try?
Well, I mean, PyTorch is a generic kind of like deep learning framework, right? And it basically, again, has like the components to assemble neural networks and various other kind of like deep learning models. So I guess any kind of like modern machine learning that you'd want to do, be it kind of like fancy GPs or just like large scale neural networks, certainly obviously transformers and various other things. So really like a Swiss Army knife of any kind of like ML or deep learning aspect. I do want to say that like for PyTorch provides like the core probing framework, and you can build on top of that. I do think that like in terms of like probabilities and support for that, I do think that PyTorch is maybe not as strong as say like something like JAX is these days, just because it hasn't necessarily been the focus, right? Like
what do you mean by probabilities here? Do you mean distributions?
Yeah, distributions and kind of like just functionality for computing various KL divergence and so on. I mean, PyTorch does have those features, but it feels like these are kind of like more well supported on the JAX side. And I think that's partially just because PyTorch, because I think I guess the audience for like the standard deep learning, let's fit like a large neural net on like a whole bunch of data, is just much larger than kind of like say like the Bayesian machine learning community. And so I think it's just like a matter of priorities. But yeah, so basically, like in a nutshell, basically like PyTorch, if you want to do really any kind of like modern deep learning, it's sort of like a foundational programming language for that. And then you can go out and like have a gazillion packages built on top of it for particular applications. You know, GPyTorch and BoTorch being one of them or two of them.
Yeah, yeah, exactly. So, folks, basically, if you want to try a neural network, PyTorch is definitely a great way to go. And then if you want to combine GPs with neural networks, as we just talked about before, you can definitely give GPyTorch a try. And yeah, I can confirm that this can be very powerful combination. It really depends on the use case, also on how interpretable you want your models to be, on how big the data are. So it depends on a lot of things. But I think if you are in such a use case, this is definitely a very powerful combination. And actually, I wanted to ask you also, like concretely, if we come back to BoTorch, how did that, come up at Meta? Like, what concrete problem, if any, inside Meta triggered the first commit to BoTorch, and also how did you make the case to open source it? Because that's really awesome, and of course I'm very sensitive to that, but I know it's not always the case.
Yeah, so I mean, BoTorch really was born out of the need to have more flexibility to enable our research and accelerate our research. So we were doing Bayesian optimization before BoTorch. We had a different stack. At the time, we were leveraging GPy, which is another GP library, and had some custom optimization code that was built on top of that. And that worked fine for like the basic problems and just fitting a model and doing Bayesian optimization. But it was really hard to try out new ideas. We had to work around the limitations of the setup to do custom things, like even simpler ones, right? Kind of like trying a non-standard kernel, or like using a different like optimization strategy. It wasn't using differential programming, so again had to implement gradients by hands if you wanted to do anything. It was just like very slow to iterate on the R&D that we wanted to do. So basically that was the state. We were doing Bayesian optimization for things internally, and it was kind of like a pain to make the research progress. And so I started a bit of a side project at the time, and I was looking into how you could resolve that issue. PyTorch was around then, but it was still the relatively early days. So we're talking, this is early 2017. I think the first PyTorch release was like, I don't know, 2016 or something. PyTorch was a meta project, that I mentioned that before, and so it's very natural to look into it. I had found those initial alpha versions of GPyTorch that I messed around with that seemed promising. Reached out to the authors, and we had some great discussions. And it seems like it was a good fit. And so after some time, I put together some proof of concept, and it pretty quickly became clear that like we had something interesting there, right? It was just so much easier to try out new research ideas, given the modularity that I mentioned earlier. And this is like when we knew that we wanted to put some more effort in it, adopt it for our use internally, and then also open source it. And why open source it, and how to make the case, I guess. Well, fortunately, Meta has a great open source culture. I mean, there's many examples for that, right? There's like PyTorch, obviously, more recently Llama, of course, but there's a lot of other stuff as well, like React Native, Presto, all kinds of like great open source packages. So the whole culture it was just conducive to this, and the culture on the team, on the Narrower team, like aligned as well. So my team had done some open source releases before. For instance, you might be familiar with Profit for time series forecasting. This is something that Ben on our team had done prior to BoTorch. And so anyway, it was like quite an easy environment to get leadership support and also like get through the necessary legal reviews. And yeah, so that was kind of like how we got the buy-in, and fortunately we were also able to like work closely with the PyTorch folks on shepherding BoTorch into open source. You know, I mentioned it's part of the PyTorch ecosystem, part of the PyTorch GitHub org, and you know, shout out to Sumit and Joe, who we worked with at the time, to get this out and have their support for that.
Let me show you how to be a good BITESIZE.